Well, hello, everyone. Thank you all for coming. Again, I'm Dávid Papp, and some of the work that I'll talk about today is based on, it's a joint work with Maria Davis, who was a PhD student of mine, graduated recently, and my current postdoc, Anita Varga. There's also a bit of introductory material here. And I should say, I should have started by saying, thanks to the organizers for inviting me. I'm really not an optimal transport expert, so I'm not even sure how I ended up here. But it's the sum of squares morning. And so my background is in convex optimization, numerical algorithms, efficient, like computational math in general, and I dabble in various applications where that's useful, from automated theorem proving to medicine. And so one of the things I've done a bit of work on is sums of squares. And I know some of you have even seen more or less this talk or parts of this talk, and some of you may be not familiar with this at all. So I try to include a little bit something for everyone. So I hope that I'm not insulting anyone's intelligence if the introductory part is too basic or whatever, but just let me know. So let's get started. So again, I think most of you are familiar with sums of squares optimization, but just very, very briefly also just to introduce notation, etc. What are we talking about? So sums of squares, mostly when we talked about sums of squares functions, we actually talk about sums of squares polynomials, right? The basic notion is the polynomial is sums of squares. If, exactly as it says on the tin, it's a sum of squared polynomials. They are obviously non-negative on our end. This is why we like them, or it's part of the reason why we like them. Often we want not just non-negativity over all of Rn, but over some subset. This could be, for instance, a semi-algebraic set defined by polynomial inequalities. Gi of x is greater than or equal to 0. And then the natural generalization of the sums of squares idea is this sort of weighted sums of squares, which I'm going to denote with this sigma with all its subscripts and superscripts. So again, what we are doing here is take a weighted sum here, where again, each of these SI polynomials, these are sums of squares, so they are obviously non-negative everywhere, and then each of them is multiplied by one of these polynomials, Gi, whose non-negativity defines the domain of interest. So these are obviously non-negative. And just because I say, weighted, of course, we could have all kinds of redundant weights in there that's sometimes useful, for example, for various reasons, including theoretical reasons. We like to include an unweighted term all the time, even though, the adding here explicitly the representation 1 is greater than or equal to 0 is kind of silly, but we need the unweighted sums of squares. And so one of the reasons why these are popular is because they are fundamental in polynomial optimization. And even when we talk about polynomial optimization, different people mean different things. These problems come in different flavors. So again, just very quickly, let's talk about what do we even mean when we talk about polynomial optimization. One flavor, this flavor one is what we have seen already in some of the lectures today, is this global optimization of polynomials. When we are given a polynomial and we want to find a minimum, or or maybe like a lower bound on its infimum or something like that, or more generally, right, minimize some polynomial over a semi-algebraic set, right? So here, all of the polynomials are given. We are trying to find an optimal value, sorry, a sharp bound on its optimal value. And this, of course, can be a non-convex problem, and we often mention, this is NP hard and it's non-convex difficult. Again, the non-convexity isn't really the reason it's difficult, right? I can actually write this as a single variable convex optimization problem, nothing simpler than that, and it's still equally hard, at least if I'm only interested in the optimal value. That's the other thing, there's quite a few applications when we're only interested in the optimal value, and in other times we really want to get one of the optimizers too, and those two problems are very different. But if you're only interested in the optimal value, then I could say this is the same problem as the following single variable problem. I'm looking for the largest constant c that I can subtract from my polynomial f, and the resulting polynomial is still non-negative everywhere on omega, right? And this is a convex optimization problem because my objective is obviously just a linear function, and my only constraint is a convex constraint, right? Because the set of polynomials that are non-negative on omega is a convex set regardless of what omega is, okay? So, but obviously this is just as hard as the original problem. There's another flavor of polynomial optimization, which is arguably even harder. And that's when we are optimizing a polynomial in the sense of trying to find an optimal polynomial that satisfies all sorts of constraints. And this becomes similar to this first flavor when at least one of the constraints is that this unknown polynomial or some affine transformation of it must be non-negative on some domain. Okay, so now I'm not given a polynomial. It's a little bit like, sometimes people call this polynomial optimization with tunable coefficients, right? In the previous flavor, I could only play with the constant coefficient. I was given a polynomial, I can mess with the constant coefficient. How can I make sure it's non-negative? Now I can mess with all the coefficients at the same time. All right. And I should mention, I mentioned this later too, obviously when we are interested in solving large-scale problems like this, there are different asymptotics to consider, right? The number of variables is very important. Obviously, the degree of the polynomials is also very important. Most of what I've been doing focuses on when the degree is high. And that's in particular interesting when these polynomials are not, like the original problem data might not even be polynomials, or the original problem definition doesn't involve polynomials, but involves some continuous functions which are ugly, and I have to approximate them with polynomials, and so naturally I'm going to use some high-degree polynomials to do this. All right, so again, this is just the previous notation again, just so we remember, and just mentioning that, yes, these polynomials are evidently non-negative on omega, so we can think of this as like a non-negativity certificate. Another way to think of this is a restriction, right? We have the set of non-negative polynomials, which is what we would really want to work with, but we can't. We are considering now a subset, right? It's like the opposite of a convex relaxation. And one of the things, of course, we need is that this is a good approximation. Otherwise, what are we even doing? And so there's all sorts of results related to this, which are collectively called Positivstellensatz theorems. Again, I'm not going to talk about this in detail, but the point is that there is a lot of literature on how these sums of squares polynomial cones can be a good approximation of non-negative polynomials. Okay, and this is under suitable assumptions either on the set omega itself, like compactness, etc., or its representation. All right. And so the reason why we like these computationally is because at least the consensus or the conventional wisdom is that this is supposed to be more tractable than non-negative polynomials, and which is essentially true for moderate degrees, although once the degree is high, this is a questionable statement. So again, why is it more tractable? It's supposed to be more tractable because we can solve SOS optimization problems using semi-definite programming, right? This is the standard thing, and we've already heard about this today, also from the dual side, right? With moment problems, right? These lead to semi-definite programs. And again, just probably many of you have seen this before, but just again, very, very quickly to run through this. And by the way, this also works with all kinds of functions, not just polynomials, right? That if we fix a basis for the functions to be squared and summed, then if I have this function s, which is a sum of squares, maybe I'll just point it in my hand. So if this is a sum of squares, so it can be written as a sum of the squares of the ri's. Each of these ri's are in the span of this basis. I can just, with some quick algebra, get to this quadratic form. Here I have the vector of my basis functions, and in the middle I end up with a matrix which is basically a general positive semi-definite matrix whose rank is the same as the number of terms. Okay, so this is why this function s is a sums of squares of functions from the span of this space, the span of that basis, if and only if there exists a positive semi-definite matrix with which the left-hand side is equal to the right-hand side. And so in particular, if I want to now really turn this into a semi-definite program, write everything in a finite dimensional representation, then we can also fix another basis. This will be the basis for the SOS functions, right? Like where the sum of squares functions live. And then we simply end up with a constraint like this, that the coefficient vector of our function, or like this boldface s, is the coefficient vector of a sums of squares function if and only if there exists a positive semi-definite matrix whose image under some linear map, this is the important thing, this is a linear map, is that coefficient vector. Okay, and this linear map is computed and can be actually easily computed from the two bases. So once I'm given the basis of the polynomials to be squared and summed, and the basis for the sums of squares polynomials, if these bases are fixed, then I have a fixed linear map here. Again, this is a lot of notation, but the gist really is that the main constraint, which is that s is some SOS function or a weighted SOS function, just translates to a set of linear equations and the linear matrix inequality, right? We need from an optimization perspective, we have to introduce this like an auxiliary variable, like an extra decision variable is this positive semi-definite matrix S, and then we have a bunch of linear constraints. And this is true also in the previous slide. I just assumed that we only have one weight, or there's no weights, but this works even in the weighted sums of squares case. And the important thing is that this linear operator A is something that can be determined and easily computed once we fix all the bases and the weights and everything. And if you've seen it, we've probably seen this in the literature, assuming that everything is monomial. That's how you end up with these nice like Henkel matrices describing this A operator, but everything is completely analogous no matter what representation we use. Okay, and so in principle, then we can just solve all these problems using any all-purpose SDP solver. So again, looking at like the first polynomial optimization flavor 1, right? We started out with this, let's say we're trying to minimize this polynomial f over some, let's say, compact omega, so we know that the minimum exists. Is the same as the largest constant c, such that, sorry, this is missing. This should be f of x greater than or equal to c for x non-negative. Sorry, there's some, it's all the right characters, just the permutation is wrong. And so this gets then approximated by, let's find the largest c such that f minus c is weighted sums of squares. And then using what we had in the previous slide, this becomes the semi-definite program on the left, right? We are finding the largest c such that, and these linear equations and linear matrix inequality describe this constraint. All right, and then as always in optimization, if you have a nice convex optimization problem, you have a dual problem, and you're usually trying to solve both at the same time to get a near optimal solution and the certificate that it's near optimal. And this is what the dual looks like. So here, and basically everywhere, the bold-face vectors all represent just coefficient vectors, right? So like I started with the polynomial f, and then over here, this bold-face f is like a coefficient vector of my polynomial f in whatever basis I chose in the previous slide. Similarly, this 1 is just the coefficient vector of the constant 1 polynomial, for example. All right, and just one more bit of notation. This A star, this is the adjoint of this operator. And so in principle, we can use any general SDP solver to solve these, but this could become a large-scale problem, in particular when the degrees in the weighted sums of squares become large, and that does become a problem. And actually, I inserted this slide. I like to put this slide in all sorts of talks. It's one of my pet peeves about the complexity of the SDP. We hear a lot of this. I hear a lot, and I've seen this in papers too, peer-reviewed papers too, and of course, definitely at conferences you hear it in talks that semi-definite programs are great because they can be solved in polynomial time, and that's just not true. That's just a statement that at least we don't know if it's true, I guess, is what we should say. So it's true with like the right definition of problem size. So if you're familiar with ideas like ellipsoid method, it's true that we can solve semi-definite programs in polynomial time, but in the size of the input, but the input required for things like the ellipsoid method includes other things than the problem data. So like if you just think of like what's the problem size here, the problem data is the f vector and whatever I use to describe this A, maybe like a giant matrix that has all the coefficients that describes this linear operator. If that's the problem data and we are interested in algorithms polynomial in the bit size of that data, then none of the methods that we know for semi-definite programming are polynomial in that bit size. This is true even if we restrict it to just SOS SDPs. Again, I'm not saying it's not true. I should say it's an open problem, right? We don't know. In particular, we don't even know if recognizing feasible SDPs is in NP or not in the bit model. So in particular, even a simple argument doesn't work that, well, if I have a feasible solution, that's an obvious, easily checkable certificate. Just give me the feasible solution. I'm just going to plug it in and check if it's a feasible solution. Even that doesn't hold because there are really simple, elegant constructions, like there's a famous one by Hachian, which only uses 2x2 semi-definite matrices, where all feasible solutions have exponential bit size. So I can't even give you a feasible solution for you to verify in polynomial time. You can't even read them. Okay, so all that theoretical troubles aside, we do have really good SDP solvers. So in principle, we can take all these problems and just solve them. Again, at least as long as the degree is small enough, these tend to work really well. And again, from my perspective, high degree is the interesting part in particular, even if the original problem doesn't involve any high degree polynomials, because remember, in order for us to get a good approximation of non-negative polynomials, by weighted sums of squares, you might need much higher degree polynomials in the sums of squares than what we have in the original problem. Okay, and right, so like from this positive Stahlansatz. And at the same time, really, we have a lot of different tools. It doesn't even matter what language you prefer, you know, MATLAB, Julia, Python, Sage, everything. There are very good packages for this. So are we done? So I thought I'll do just a very, very quick MATLAB demo. And sorry, this is just way too much text in one slide. But I just wanted to pick a really simple problem that we already know the solution to. And it's this sort of Chebyshev approximation problem, right? The classic problem, find a monic polynomial of some given degree with the smallest infinity norm on AB. Right? This is well known. For example, for -1, 1, we get an appropriately scaled Chebyshev polynomial. This particular problem is a little annoying for my numerical demonstration because the objective function value depends on the degree and it tends to 0 very quickly. So instead we'll do -2, 2 because then the optimal value is just a constant 2 no matter what the degree is. It's just easier to check if what we are doing is fine. And I want to mention this is already as simple as it is. It's already a flavor 2 type of problem, right? Because now we are not given a polynomial, right? We are trying to find an optimal polynomial. And our constraints will be that the polynomial is less than or equal to the bound that we are looking for, and of course also greater than or equal to the negative of the bound that we are looking for. So we have multiple SOS constraints, but just on a univariate polynomial. I have the details of this, but I think that I only put this here in case there are any questions, but I think you understand it. And then we can just quickly run this. So what I did here, again, the details don't really matter. I just use one of these existing tools. This is a YALMIP inside MATLAB, where there is just a really straightforward way to write. For example, you know, I can declare that I have a polynomial which is required to be sums of squares. Just a very, very straightforward way to write down this problem, and then we can solve it. And we find in basically no time, you can even plot the solution. It looks exactly what it should look like. This is perhaps less important. And we know that the optimal value should be 2. We get approximately 2. This is looking really good. By the way, the semi-definite programming solver I used is Mosaic, which is a really good solver. And it works fine. So this was degree 13. If I increase the degree a little bit, I still get a basically instantaneous solution. You can see it's looking a little bit wonky. I don't really like it. I don't really like the optimal value either. And what I like the least is that Mosaic thinks that it solved the problem. So it really thinks that we have a primal dual feasible solution. Everything is optimal when we know that it's getting far from it. And if I increase the degree just a little bit more, now I just really get basically garbage. But also, at this point, the solver also realizes that something is wrong. So it didn't take long as I was increasing the degree. There's no issue with computation time. It's just that as soon as I go above degree 16 or so, I'm having all sorts of problems, numerical problems. So let's talk about why that happens. I think the easiest way to understand it is from the dual side. Remember, this was the dual problem, where the constraint that these this Y matrix is in the dual cone, the dual of the SOS cone. This translates to some constraint that the image of, well, here I put Y, here I put YI, it's a confusing notation. What we really have here is not just a single giant matrix, but rather a block matrix with several blocks. Anyway, so each of the blocks of this matrix has to be positive semi-definite. So we are given some linear map, and under that map, the image of my dual vector has to be positive semi-definite. And the issue is that when all of the polynomials are represented in the monomial basis, then all the blocks of this A star of lambda are Hankel matrices, which are notoriously bad to work with numerically. In particular, every positive definite Hankel matrix of size n has a condition number that's bounded from below by some function exponential in n. Okay, so any method that is, for example, trying to stay in the feasible region and iterate towards an optimal solution will be iterating from one ill condition matrix to another, and so it's bound to have issues before we get to very high degrees. So this is a really small problem, but we are still having numerical issues. And In this talk now, I'm just going to advocate for interpolants. It's definitely not the only thing we can do, but generally speaking, the point is this doesn't mean that we can't solve these problems for high degrees. It just means that we really need to think about how we represent our polynomials. And using interpolants or a suitable orthogonal basis or something can really help a lot. So again, this is kind of the general principle, just use better bases. And this is why I was showing you earlier how we went from sums of squares to the semi-definite programming representation, because I really want to emphasize that that's equally easy no matter what basis we use. Okay, so we're really not stuck with monomials. So in particular, again, perhaps we don't have to go through like all of the excruciating details here, but if we want to figure out what this A operator is for interpolants, it's really simple, easy to do it based on that same derivation that I showed you before. Again, this is just for the unweighted case. We end up with a representation of this A operator in terms of matrices, which are all just rank 1 matrices whose computation requires that we basically just have to evaluate our basis polynomials at the various points where we are sampling our functions. Okay, so this is just, with just sampling, we can do it. Plus, because these matrices are rank 1, this will actually also help with efficiency in addition to conditioning. Of course, still, even just to evaluate these coefficient matrices, we do need to evaluate our basis polynomials, so which shows that even both bases are important, right? So remember, I was talking about the basis of the polynomials to be squared, and then the basis for the sums of squares polynomials. When I say let's use interpolants, what I really mean is the higher dimensional basis, the basis for the sums of squares polynomials is an interpolant basis. And here what I'm saying is for the other basis, for the basis of the polynomials to be squared and summed, that P basis needs to be chosen in such a way that point evaluation at the samples is reasonably well conditioned, so we can actually compute these matrices accurately. Again, we can do this, of course, in the weighted case, also for multivariate polynomials. For some applications, it might be interesting to also use Hermite interpolants, where we don't just have function values, but also derivative values. All of this can be done. The biggest challenge, specifically if we are going to use interpolants, is that we need to find good interpolation points. And multivariate interpolation, of course, is difficult and still largely unsolved in very high dimensions. And so, again, just to very quickly try, so we can now solve in MATLAB the exact same problem as before. Same everything. The only thing that will change, I'm even using the same semi-definite solver, very importantly. The only difference is that it's set up using interpolants instead of using the monomial basis. And this is, again, the same like low degree. But the point is that now I can go to much higher degrees. And it takes a while. I mean, this is still like a second. And I'm getting really, really good results. I can try to increase this even further. The issue is if I start increasing the degree, I have to keep you entertained by talking, because this is still just working. So you see now we're starting to have another problem where we can manage the high degree numerically, but it's taking a while. In fact, this is taking longer now that I'm live on camera than it did when I was just trying this. But I was able to solve it on this laptop for degrees around 400. And around 500, I would run out of RAM in this laptop. That's really the next sort of issue. I might just have to try and abort this if I can. Yep, this is now an incorrect result because I aborted it sooner, but I wanted to show you at least some higher degree. Okay, so I can go above degree equals 100, for example, which was nowhere close to what we were able to do before, but it looks like, okay, even degree 200 ran in a couple of seconds. But you see, the issue is as soon as I went a little bit higher, it was just taking forever. So it seems like we managed the numerical problems, but now we have a new problem, right, which is just the complexity of all of this, right? It takes too much time, way too much memory. Again, the crazy thing is that, if you just think of it as it just from the perspective of like convex optimization, like it's something like degree 500, this is a small convex optimization problem, right? I'm still just optimizing over a whatever 500 dimensional set or something like that. For convex optimization, that should be like nothing, and yet I'm running out of memory, right? And that's simply because these SDPs are gigantic, right? Even in the univariate case, right, if I'm, say, optimizing over univariate polynomials of degree 2d plus 1, my semi-definite program has order of d squared number of variables. And that's really what's giving me all of the trouble. And in particular, if I'm going to use an all-purpose interior point algorithm, I think I haven't introduced this notation yet, interior point algorithm for SDP, that, for example, what's built into the solver Mosaic that I was using, say like in this univariate case will require order of d to the 4 floating point operations, which is just a lot, right? D to the 4.5 complexity in total, which is, I mean, it's polynomial, but it's a lot. And it's more than it sort of should be. Like, so if we are thinking of like, in general, something like an interior point algorithm, any kind of Newton type algorithm, I would expect that most of the cost per iteration is a Newton iteration, right? Which should be d cubed, but I'm getting d to the 4. And the reason I'm getting d to the 4 is because I have too many variables. Okay, so in principle, we should be able to do something with this. And there are many things we could try to do. One approach would be to just focus on a subset of problems. If we have very large problems, hopefully there's some kind of structure like sparsity or something we can exploit. We have some ongoing work in this area, but I'm not going to talk about this today. Another thing we could do is, we only talk, if we only talk about sums of squares because it's a good approximation of non-negative polynomials, then of course we could just talk about entirely different subcones. Everything that I'm talking about today in the second half of the talk applies to all these other things, if you've ever heard of them, Song polynomials or Sage functions and so on. Everything I'll talk about applies to all of these as well, but otherwise I won't really talk about them today. Yet another possibility would be to stick with SOS, stick with semi-definite programming, but exploit some special structure, if there is any, in the semi-definite programs that come from polynomial programming. Looking at the program, I think there might be a talk coming up that will do exactly that. I will not talk about it. But this is, Lorraine is a semi-definite programming solver that does exactly that. And instead what I'll talk about, just in the bottom of the slide, let's stick with SOS, but try to ditch the SDP as much as possible. And so, because why do we need to use SDP? We only did this because, well, that was that sort of readily available representation of sums of squares polynomials in terms of linear matrix inequalities. But in principle, we could be working at this level where, we have, this is what's called a standard form conic optimization problem, or like a convex optimization problem in standard conic form. Linear objective, linear constraints, all the complexity of the problem is pushed here. K is some well-behaved, closed, convex, full-dimensional cone. And then there is an appropriate dual problem, which looks like so. Something called a dual cone appears here. Some of you might be familiar with this. So the idea is that what we are really trying to do in all the flavors of polynomial optimization, or specifically sums of squares optimization, is problems that look exactly like this, where the cone K is a weighted sum of squares cone, or perhaps the Cartesian product of weighted sums of squares cones, and maybe some other sort of nice cones. And so this is what we call a non-symmetric conic optimization problem. This would be a symmetric conic programming problem or conic optimization problem if this K was something like the non-negative orthant or the cone of positive semi-definite matrices, right? Semi-definite programming. But in principle, we could put here whatever cone we want and try and solve that problem, or develop algorithms that solve these kind of problems. Of course, the issue is that, especially once K and K star are different, generally what we need is that both of those cones are really well behaved. We have to understand them, as well as we do, say, semi-definite matrices. And that's generally not true for most cones. And what's worse is that even then, there's just very few algorithms in the literature, and even less in terms of actual software. For semi-definite programming, I can pull off the shelf, half a dozen free solvers that work really well. As soon as you start putting here any kind of non-symmetric cones, there are very, very few options. So this is one thing that I have been working on for a while. Non-symmetric cone programming algorithms that work very generally enough that we can use them for SOS optimization. So again, why is it difficult when we try to do SOS optimization in this method? So again, the obvious thing to do is see what works for something like linear programming or semi-definite programming and just try to do the same, only a bit more generally, right? So what works the best, both in theory and in practice for these problems, is so-called path-following interior point algorithms, which again, I'm sure some of you are familiar with, but maybe some of you aren't, so here's just a very quick recap how these work. sorry, I'm forgetting how much time I have.
Until 12:30.
12:30? Okay, thank you. So the basic idea of these methods is that, so this is the original problem we want to solve. Let's say we just focus on the primal, and I forget the dual for a moment. This is what we want to solve, K, some cone. And instead we look at this kind of penalized problem, or it's kind of like a penalized problem. I remove the explicit x belongs to the cone constraint, and I put here instead this function. This is not the same f as before. I hope the notation is not confusing. F is something that we call a barrier function. It will need to have all kinds of properties. First of all, let's make sure that f is defined on the interior of the cone K. So basically, implicitly, I still have the x belongs to K condition, but it's just implicit now. F is only defined on the interior of the cone K. And as I approach the boundary, the function value tends to infinity. So no matter what mu I choose here, any positive mu will ensure that I will stay inside the interior of the cone. And let's also choose f in such a way that it's strictly convex and twice differentiable. Then I have a strictly convex, twice differentiable objective function here. I just have linear constraints here. Assuming that there is a minimum, just waving my hands, assuming that a minimum exists, it's unique. It's well defined for every mu. And the basic idea is, let's maybe just approximately solve this and keep reducing mu. And as mu tends to 0, I should be approaching the optimal solution. And this doesn't obviously work. But if we choose the right kind of barrier function, again, lots of hand waving. This goes back to something called self-concordance theory in the 1990s by Nesterov and Nemirovsky. If we use the right kind of function f, then we can say a lot of nice things. One is that as mu approaches 0, the sequence of these optimizers exists, and it is the optimal solution of the original problem, right? Which is what we want. Moreover, we can also bound how far we are in terms of objective function value from the actual solution that we are looking for. This is also important. Otherwise, you can't get a theoretically efficient algorithm. Okay, so this is what we generally do: linear programming, semi-definite programming, and so on. For example, in linear programming, this is the f that everybody uses. For semi-definite programming, this is the f that everybody uses. And the different methods in part differ in exactly what are we going to do with these auxiliary problems, right? Because of course, what I don't want to do is actually solve this to optimality, for example, for a given mu or something like that. But I'll just solve this approximately, then I reduce the mu, then I use the previous approximate minimizer to go towards an approximate minimizer of the smaller mu, and so on. All right, so we can also turn this into a dual method or a primal dual method if we have the right kind of barrier for both of my cones, right? So now going back to general non-symmetric cone programming, I have two cones, K and K star. Ideally, I want to solve the primal problem and the dual problem at the same time. And if I have the right kind of barrier, again, these are called self-concordant barriers. If I have that kind of a barrier function for both cones, then at least at a high level, I should be able to figure out an algorithm that will do this, and everything should work. Surprisingly enough, that's still not easy. So there is still quite a bit of literature on how to make that work. But I won't even talk about that, because the biggest issue is we do not have such a barrier function for the SOS cone. So it looks like we are dead in the water because, or like right at the outset, we can't do anything. We do have the nice, the well-behaved barrier function for the dual of the SOS cone, but we don't have it for the SOS cone. Okay, so this is at least it's an open problem whether there is such a function or not. And that's particularly an issue if we really want to compute, say, like an optimal SOS polynomial, not just the optimal value, because then I can't just say, well, let's just work with the dual. I can figure out the dual optimal value approximately, and that's it. I really want to solve the primal problem as well. So lacking the self-concordant barrier for sigma, the best thing we could try to do is to only work with the dual barrier and derive some algorithm that solves both the dual and the primal problem at the same time, even though, using similar ideas as what I presented you earlier, even though we only have one barrier, which again, it's one of those things you have to try to see why that's hard. It's very difficult. So even though all of this self-concordance theory is from like the 1990s, it took until 2014 before the first algorithm like this came out by Anders Kaja and Yin Yu Ye. This was, at least to my knowledge, the first interior point algorithm for non-symmetric convex optimization, which works only with one barrier. And even then, it took until 2017 till the first actually complete and correct analysis of the method came out, because the original has some issues. And for a long time, that was basically the only thing. So if you want to, for example, run this method, there are existing implementations, again, in MATLAB as well as Julia. Full disclosure, this is mine. This is not mine, so of course, I recommend the first one. But also, there are various problems with this method too. We have a newer one which fixes some of those problems. Again, won't really get into the details of this, but we have also this new interior point algorithm which avoids all kinds of issues with like line search and predictor corrector steps. It's a much simpler algorithm. That's what I would just say in short. Easier to implement, easier to analyze, and gives you the same complexity bounds and everything as all of the previous methods. In particular, even if we were to specialize this back to something like linear programming, the asymptotic complexity is still the same as that of the best known interior point algorithms for linear programming. Okay, so let's do this one more time. So I used the solver Alfonso to solve the exact same problem. And remember where we were, it was that we could, like there were no numerical issues solving these problems for low degrees, but we just couldn't do it for high degrees because we ran out of memory. So if I try to do the same thing, I get the correct objective function value for low degrees. But the point is that now I should be able to increase these degrees to much higher. And you see that in a couple of seconds, right? But I was just not able to run at all because I was running out of memory and I had to keep talking while we were waiting for the results. We can easily solve these problems. Maybe 1,000 is going to take a little bit too much, but it's just iterating way, way, way faster than the previous one. So this uses an order of magnitude less memory and at least an order of magnitude less time because it avoids that squaring of the number of variables, right? That blow up of the semi-definite program. So again, theoretically, basically what's happening, the main thing that's happening is that the per iteration complexity is reduced by a factor of d, which obviously for like d equals 1,000 or something, that's pretty big. Iteration complexity is the same as before, so this is what the overall complexity looks like if you want like an epsilon optimal solution. And then for this last part of the talk, I'm going to kind of switch gears a little bit and talk about, I mean, it's something related, but somewhat orthogonal to the previous things. So one of the issues with this whole non-symmetric conic approach could be that someone might really actually want to solve the SDP, right? One could say the only reason we have been using SDPs to solve SOS optimization problems is not just because, well, that was just readily available and we have SDP solvers, so why not do it? But because, for example, I'm interested in a little bit in automated theorem proving. And one way to do that with polynomials is that you need to show that ultimately the problem boils down to showing that some polynomial is non-negative. And how do I prove that? I prove it by showing you an explicit sums of squares decomposition. How do I get that sums of squares decomposition? I get it from the optimal solution of the SDP, right? I have to take that positive semi-definite S matrix, which I computed, which has to satisfy, this, right? Which I can easily check. Suppose this S is actually a rational matrix now, right? Maybe I worked in exact arithmetic, or maybe I worked, numerically, but somehow I figured out a rational matrix S that satisfies this. And I can check with a square root free LDL decomposition that it's really positive semi-definite. And that's what will really show that this is a non-negative polynomial. So trying to circumvent the semi-definite programming formulation seems kind of pointless. But the interesting bit is, and that's what kind of this part of the talk is about, is that from the right primal dual pairs, we can actually reconstruct the solution of the SDP in closed form. And this is cheap too. It doesn't cost more than a single iteration of the interior point algorithm. So not only can we avoid that blow up if we are not interested in the solution of the SDP, but in a sense, we can solve this simpler problem and then blow up the solution to the solution of the SDP. Okay, and we can use this to prove that, say, like our computed F minus C is sums of squares. First, I'll show you at least high level the details of how it works, and then I'll show you why I think this is particularly interesting. So again, just recall this was our characterization of the SOS cone, right? It's the set of those vectors that are the appropriate linear image of this positive semi-definite matrix S, and then we have the dual representation. Again, some of the details are not as important as others. There's some more notation. We need a particular function related to the dual cone. The point, though, is, so suppose we have a coefficient vector S. This now doesn't have to be a sums of squares polynomial. It's just a candidate. Okay, it's in the same space of polynomials. And suppose I have any vector from the interior of the dual SOS cone. Now I have this closed form formula. It takes a while to compute, but it's a closed form formula, and I can do this in rational arithmetic if I want to. Like if this was a rational coefficient vector and this was also a rational vector from the interior of the dual cone, this can be a rational matrix. And it's given in closed form, and it automatically satisfies these equations, right? Which was one of the two parts of showing that S is SOS. And moreover, this matrix that we just constructed is positive semi-definite if and only if this relation holds. Again, I won't go through the proof or anything, but the important thing is, again, this is easily constructible. This is automatically true. Of course, if I'm working with rational vectors, I can also just verify it, no problem. But also this I can easily verify. Okay, because I'm only working, everything I'm doing here, everything that's complicated here is associated with the dual cone, and the dual cone is where I can work. I have my barrier function. This is actually my barrier function. I need its Hessian, which I can just do with calculus. I can compute everything here. Okay, so suppose that this vector S in fact belongs to sigma, and suppose that somebody somehow gives me a vector Y for which this matrix is positive semi-definite, that's something that I can verify, either by just explicitly constructing this and factoring it, or I don't even have to do this. I never even have to go through this formula. This is just part of the proof. I can just compute this expression, which requires a lot less time and especially memory. And all I need to check is that this vector belongs to the dual cone, which I can. Right? So I don't have to solve a semi-definite program or anything. This is all just, the point is this is all just linear algebra. Okay, so if I have a vector S and a vector Y, and somebody tells me this relationship holds, I can verify that claim with just linear algebra. This is really cheap and easy. All right? And if it's true, that proves that my coefficient vector S is the coefficient vector of something from sigma. Okay, so I proved that something is sums of squares without even explicitly constructing a sums of squares decomposition. If I need to, I can use this to construct a sums of squares decomposition, but I don't need it. Okay, so again, motivated by this, I'm going to say that if we have such a vector Y, we call this a dual SOS membership certificate. Why? Because it's from the dual cone and it certifies membership in the SOS cone. Of course, all of this would be moot if this didn't necessarily exist or something. Like everything I said here could be vacuously true, for example, right? Maybe such a Y doesn't exist or something like that. But exactly on the contrary, let's fix a polynomial S, and now I'm choosing this to be actually sums of squares. In fact, let's choose this from the interior of sums of squares. And let's look at, so what I'm defining here is the set of all of its dual SOS membership certificates. And what we have shown is that not only is this non-empty, it has a non-empty interior. Right? This is a full-dimensional subset of the dual cone, of the dual SOS cone. The full dimensional is important because that means we can, in principle, find numerical, we can use numerical methods to find an element in here. Okay? And I want to contrast this. So not only have we avoided blowing up the problem size and solving the SDP explicitly with the numerical method, one could argue this is even better, theoretically speaking, because again, what I'm doing with something like MOSEC or any SDP solver is I will find in the SDP formulation a positive definite matrix S that approximately satisfies my linear equations, right? S equals A of capital S. But this will only hold true, approximately. So what I'm really doing when I solve the SDP is I'm computing a sums of squares certificate for a polynomial that's very close to the one I'm trying to certify to be non-negative, but it's not the same. Whereas what I'm doing with the dual certificates, this is less work, and I'm computing something that's an exact, accurate certificate. Okay, and at the same time, because it's a full dimensional set, I can do this purely numerically. How should we do it? This is now this part where I would have a slide on, so what sort of numerical, let's develop a numerical method that, say, for a given polynomial, for a given SOS polynomial, computes such a dual membership certificate. Turns out we don't even need to compute, figure out any new methods. All the algorithms this is true in the Skaya and Ye paper, the Alfonso algorithm, also this new algorithm I mentioned, all of these automatically yield such primal dual pairs. Again, I won't get into the details, but basically the point is that even to derive all these statements I mentioned here, like where this formula comes from and the fact that this is a full dimensional set, etc., all of this is using this self-concordance theory from convex optimization. And so one of the byproducts of this is that if we are using interior point methods that have certain properties, then what we are computing is automatically the right kind of dual vector. Okay, and so in fact, this last algorithm, this was actually sort of designed with that in mind. So this was the point where we already understood what, earlier algorithms just kind of coincidentally, so to speak, gave us the correct vectors. Once we understood what sets apart those interior point algorithms that will work and from the ones that won't work, we figured out that this is a simple thing that could work. Before that, we also had another efficient algorithm that's just specifically for sums of squares. This is an earlier one. I would only recommend this if you really want to work in either arbitrary precision or even exact arithmetic. So this was specifically a method for SOS optimization for those who really want like explicit, exact SOS certificates. This one was designed specifically with this in mind, like how do we avoid an exponential blow up of the sizes of the certificates and so on. But if you're just going to work with numerics, then these algorithms all work. And again, the interesting bit, I think, here is that we can work purely numerically, right? This is not even a hybrid method where I work numerically and then I have to do a lot of extra post-processing in exact arithmetic. I work numerically, I end up with this floating point vector. Of course, I can just treat that as a rational vector, which it is. And that is a rigorous SOS certificate that I can verify in rational arithmetic. So I have all the efficiency of the numerical methods, but also the accuracy of an exact arithmetic method. And so I'll wrap up here. So as far as I'm concerned, I still like SDPs and primal dual IPAs. I think that they are really good for SOS as well, as long as it scales up. The problem is, eventually you run out of memory. I think as long as you don't run out of memory with the state-of-the-art SDPs, I don't think we can beat them, especially if you want high accuracy solutions. Once you run out of memory, obviously you can't use them. And at that point, I think one either has to move towards things like non-symmetric interior point algorithms, which I was talking about, or maybe some of these structure exploiting SDPs like Lorraine, et cetera. Either way, I think that choice of representation is important. It can affect both the conditioning and the efficiency. And again, this last bit, I think this is only mainly interesting, I think, for those who are interested in certified lower bounds, like in the previous talk, for example, right? Using this in theorem proving. These dual certificates, this is sort of an infrastructure that lets us certify that we have an SOS polynomial, even without computing the explicit SOS decomposition or solving those giant SDPs. But even though we are only working numerically, we can get rigorous, rational, certifiable bounds from purely numerical computation. That's what I had to do for today. And let me know if you have any questions.